Welcome to Physics Can Be Fun with me, Stephen Thomas. We are continuing with our revolutionary physics topic, and today we're dealing with electric circuits. And in particular, we have a little electric circuit for you. Hope you can see that. And we're going to find the internal resistance of this cell. Now, I thought to myself, let's see what is the least amount of equipment we can use to find the internal resistance of a cell. I don't know whether this particular method I've thought up will work, but let's try it. This is science. Let's experiment. If we fail, we repent, we move on. So we've got one cell. You can't get fewer than that. We've got one switch, and we've got basically a short circuit. So we're just going to short circuit this, which I wouldn't do with a car battery because we'd see sparks. And we're going to apply one formula to this and see if we can work out the internal resistance. That means how much resistance is there inside the battery. We've got no resistance outside the battery. We've just got, look, we've got a wire and another wire and a piece of baked bean tin to act as our switch. So outside we've got no resistance, and the only resistance we're going to get is internal resistance inside the battery. And we're going to be using this particular formula. EMF, or epsilon, equals I in brackets external resistance capital R plus internal resistance little r. Getting rid of the brackets, EMF equals IR plus IR. Now EMF is what you measure the voltage when there's no current flowing, and then we get another thing called terminal potential difference, which is when the current is flowing. So we're going to take a few measurements and we're going to try and work out the internal resistance of the cell. Now we do it at school, and it's normally a complicated experiment. It can take one lesson or a week's worth of lessons, just depends how thoroughly you want to do it. But both those formulae are just a variation of Ohm's law. That is equal to volts. EMF is measured in volts. There you see the amps, and there you see the resistance. That's the total resistance that's external and internal we could have. Now let's measure the EMF of the cell. But first, because I've got it on that setting, I'd like to measure the short-circuited current that this cell can kick out. And then that is when we short-circuited, how much current can this cell kick out. So I've got it onto the current setting on this multimeter. So let's just, okay, watch that reading. 5 amps. So you can see that I'm just taking this meter and I'm short. An ammeter is basically a short circuit. So 5 amps flows. So let's write that down. Let's get rid of those values. And let's write what we have. Amps with a short circuit. 5 amps. That's quite a lot of amps. Now let's go and try and find the voltage of this. So we take our voltmeter and we're going to have to put this here onto there, and let's turn this onto, and now we're ready to measure our voltage of the cell. So it was kicking out 5 amps. Let's see, it's a 1.5 volt cell. Let's just put this straight across the end. .09 volts. So this cell is near the end of its life. 1.09 volts. Let's write that down as the EMF. EMF, no current flowing, 1.09 volts. 1.09 volts. And then let's now also measure when we short circuit this, when we close our switch and we just have a short circuit, what does the voltage drop to? There it's 1.09. 0.03 volts. See, the voltage climbing up again since we released it. As we kill the cell, its voltage drops. Now it's repairing itself. It's now 1,07 volts. Now let's just do that again. You see that the voltage drops to 0.03. 0.03 volts. Terminal potential difference 0,03 volts. So that's the potential difference when a current is flowing. And in fact, we have a concept called lost volts, which is the difference between the EMF when no current is flowing and the terminal potential difference when a current is flowing. And the lost volts, let's just work that out, comes to 1.09 minus 0.03. So the lost volts 1,06. 1,06 volts is our lost volts. And normally lost volts adds up to IR, I little r. But we're trying to find out the internal resistance of the battery. So let's go to, again, that formula. EMF equals IR plus I little r. EMF we've measured at 1,09 volts equals I, we measured 5 times external resistance was 0 plus, now the same current flows through the external circuit as flows through the battery because both of them are in series, plus I, which is 5 times internal resistance. So that adds up to 0. So 0 plus 5R equals 1,09. And dividing both sides by 5, that cancels out, and so we find the internal resistance is 1,09 divided by 5 equals 0,218 ohms. Internal resistance R equals 0,218 ohms. There is our lost volts, and as I mentioned before, amps times internal resistance normally adds up to lost volts. So let's take the amps times the internal resistance, which is 5 times 0.218. 5 times 0.218 equals 1,09, close enough. So this was a really simple way of measuring our internal resistance. Whether it's totally accurate or not, I can think of another experiment we could try. Why don't we just try shorting out this battery, and then when there's no voltage left, let's just get the voltage is dropping, it's on 0.2. Let's just leave it to short itself out and die, and then let's use our ohm meter and see if we can find the internal resistance of the battery when it's completely dead. I don't know if that will work. And here we have our cat, who's also very curious and interested in knowing what the lost volts is. You interested in finding the lost volts of the circuit? So here we have our cat, and he just wants to sit on my lap.